let me tell you about something that has shaken the foundations of cosmology, a discovery so baffling, so contrary to everything we thought we understood, that it has forced scientists to question the very framework we use to comprehend the universe. The Hubble Space Telescope, peering deeper into space and further back in time than ever before, has found something at the edge of the observable universe that shouldn't exist. Something that defies our most fundamental theories. Something that, according to everything we know about physics, simply cannot be there. It shouldn't be there, but it is. And the fact that it exists means that either our understanding of the early universe is profoundly wrong, or there are processes at work in the cosmos that we have completely failed to anticipate. Either way, we are confronted with a mystery that challenges the foundations of modern cosmology. I want to take you through what Hubble found, why it defies logic, and what it might mean for our understanding of the universe. Because this is not a minor anomaly that can be explained away with small adjustments. This is a crisis that demands either new physics or a fundamental revision of how we think the cosmos evolved. Let me start by explaining what it means to look at the edge of the observable universe. When we look into space, we look back in time. Light travels at a finite speed about 300,000 kilometers per second. When you look at the moon, you see it as it was 1.3 seconds ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star, Alpha Centauri, you see it as it was 4.37 years ago. The farther we look, the further back in time we see. The Andromeda Galaxy, 2.5 million light years away, appears to us as it was 2.5 million years ago. Distant galaxy clusters, billions of light years away, appear as they were billions of years ago. The observable universe has a limit. Light has had only 13.8 billion years, the age of the universe, to travel toward us. We cannot see beyond this horizon because light from more distant regions hasn't had time to reach us. At the edge of the observable universe, we see the cosmos as it was in its infancy. We see the first galaxies forming, the first stars igniting, the universe taking its first steps toward the complex structure we see today. This is where Hubble looked, and this is where it found something impossible. Now let me describe what Hubble actually observed. The Hubble Deep Field observations are among the most important images in the history of science. By pointing at seemingly empty patches of sky and exposing for hundreds of hours, Hubble revealed thousands of galaxies in regions where nothing was visible before. The most recent and deepest observations of the Hubble Ultra Deep Field and its successors peer back to when the universe was less than 1 billion years old. We see galaxies as they were more than 13 billion years ago in an era astronomers call the cosmic dawn. According to standard cosmological theory, these early galaxies should be small, primitive, and irregular. The universe was young. There hadn't been enough time for large structures to form. The first galaxies should be building blocks, fragments that would later merge to form the massive galaxies we see today. But that's not what Hubble found. Instead, Hubble found galaxies that are far too large, far too mature, and far too well organized to exist at such early times. Galaxies with hundreds of billions of stars. Galaxies with clearly defined spiral structures. Galaxies with supermassive black holes at their centers. Galaxies that look like they've been evolving for billions of years, but couldn't have been because the universe itself wasn't that old. These galaxies shouldn't be there. They defy our understanding of how cosmic structure forms. Let me explain why these observations are so problematic. The standard model of cosmology, called lambda CDM, for the cosmological constant, lambda and cold dark matter CDM, makes precise predictions about how structure forms in the universe. In this model, the universe began in an extremely smooth state. The cosmic microwave background radiation from 380,000 years after the Big Bang shows that matter was distributed almost uniformly with tiny fluctuations of about 1 part in 100,000. These tiny fluctuations grew over time through gravitational attraction. Denser regions pulled in more matter, becoming denser still. Eventually, they collapsed into the first dark matter halos, which then accumulated ordinary matter and formed the first stars and galaxies. This process takes time. Gravity works at a finite speed, the speed of light, and the collapse of structures is gradual. The first small galaxies should have formed a few 100 million years after the Big Bang. Larger galaxies should have assembled later through mergers of smaller ones. The model predicts a hierarchical assembly process. Small structures form first, then merge to form larger structures, which merge to form still larger structures. The massive galaxies we see today, like our own Milky Way, should have assembled over billions of years from countless smaller building blocks. But the galaxies Hubble found at the edge of the observable universe are already massive. They haven't had time to assemble through hierarchical mergers. They appear fully formed in an era when they should still be fragments. This is the problem. The timeline doesn't work. The physics doesn't allow it. These galaxies shouldn't be there. Now, let me discuss specific examples of what Hubble found. The first category of impossible objects is massive galaxies at extreme redshifts. Redshift is how astronomers measure cosmic distance and cosmic time. Light from distant objects is stretched by the expansion of the universe, shifting toward longer, redder wavelengths. The higher the redshift, the more distant the object, and the earlier we are seeing it. Hubble found galaxies at redshifts of 9, 10, 11, and beyond, corresponding to times when the universe was less than 500 million years old. Some of these galaxies contain hundreds of billions of solar masses in stars. They are as massive as the Milky Way, which took 13 billion years to assemble. How did these galaxies form so quickly? The standard model cannot explain it. There simply wasn't enough time for gravitational collapse and hierarchical assembly to produce such massive objects. The second category is mature morphologies at early times. Some of the early galaxies Hubble observed show clear spiral structure, the characteristic pinwheel pattern of galaxies like our own. Spiral structure requires time to develop. The disk must form, settle, and develop the density waves that create spiral arms. This takes billions of years, but Hubble found spiral galaxies when the universe was less than 1 billion years old. They look like mature galaxies that have been evolving for eons, but the universe wasn't old enough for such evolution. The third category is supermassive black holes at cosmic dawn. At the centers of most large galaxies sit supermassive black holes, objects, with millions or billions of times the mass of the Sun. Our Milky Way's central black hole has about 4 million solar masses. Some galaxies host black holes of 10 billion solar masses or more. These black holes grow by accreting matter, but accretion has limits. The Eddington limit describes the maximum rate at which a black hole can grow. If it accretes too fast, radiation pressure blows away the infalling matter. Even at the Eddington limit, growing a supermassive black hole takes time. Yet Hubble found evidence of supermassive black holes in very early galaxies, black holes with billions of solar masses existing when the universe was less than 1 billion years old. These black holes would have had to accrete continuously at the maximum possible rate since the first moments after the Big Bang, and even then, the numbers barely work. Where did these black holes come from? How did they grow so large so fast? The standard model struggles to explain it. The fourth category is metal-enriched galaxies at early times. In astronomy, metals refers to any element heavier than hydrogen and helium. These elements are produced in stars and distributed through supernovae and stellar winds. The first generation of stars formed from primordial hydrogen and helium had to live and die before metals could exist in significant quantities. This process takes time. Stars must form, evolve, and explode. The enriched material must mix into the surrounding gas. New stars must form from this enriched gas. The metallicity of galaxies increases gradually over cosmic time. Yet Hubble found galaxies at high redshift with significant metal content galaxies that appear chemically evolved despite existing in an era when few stars should have lived and died. The enrichment seems too advanced for such young objects. Now let me explain the theoretical crisis this creates. The lambda CDM model has been extraordinarily successful. It explains the cosmic microwave background, the large-scale distribution of galaxies, the expansion history of the universe, and countless other observations. It is one of the best-tested theories in all of science. But the lambda CDM model makes specific predictions about early galaxy formation predictions that Hubble's observations contradict. This is not a minor discrepancy. This is a fundamental challenge to the model. If the predictions are wrong about early galaxy formation, something basic is missing from our understanding. Several possibilities exist, and none of them are comfortable. The first possibility is that the observations are wrong. Perhaps the distances are overestimated. Perhaps the masses are overestimated. Perhaps systematic errors in the analysis have led to incorrect conclusions. This is always possible in science. Extraordinary claims require extraordinary evidence, and the evidence should be scrutinized carefully. But multiple independent observations using different techniques have confirmed the basic findings. The galaxies are real, their distances are well established, their masses, while subject to some uncertainty, cannot be reduced enough to eliminate the problem. The second possibility is that our understanding of star formation is wrong. The lambda CDM model depends on assumptions about how efficiently gas converts into stars. If star formation was much more efficient in the early universe, if gas converted to stars faster and more completely than we assumed, then massive galaxies could form more quickly. But we have reasons for our assumptions about star formation efficiency. They are based on observations of nearby galaxies and detailed simulations of gas dynamics. Changing these assumptions significantly would conflict with other observations. The third possibility is that our understanding of dark matter is wrong. Dark matter is the scaffolding on which galaxies form. Dark matter halos collapse first, and ordinary matter falls into them afterward. The properties of dark matter, its mass, its interactions, its behavior determine how quickly structure can form. If dark matter behaves differently than we assumed, if it is warmer or self-interacting or subject to forces we haven't considered, the timeline of structure formation could change. But warm dark matter and self-interacting dark matter have been studied extensively. They solve some problems but create others. They tend to suppress small-scale structure, making the formation of massive early galaxies even harder to explain, not easier. The fourth possibility is that there is new physics we haven't discovered. Perhaps the early universe was different in ways we don't understand. Perhaps there were processes operating at early times that we haven't accounted for. Perhaps our fundamental theories, general relativity, the standard model of particle physics, need modification in ways that affect early cosmic evolution. This is the most radical possibility, but it may be necessary. When observations contradict well-established theory, sometimes new physics is required. Now let me discuss what James Webb has added to this picture. The James Webb Space Telescope, launched in 2021, has extended Hubble's observations to even greater depths and earlier times. James Webb can see further into the infrared, detecting light from galaxies at even higher redshifts, What James Webb found made the problem worse. James Webb discovered galaxies at redshifts of 13, 14, and possibly beyond, corresponding to times when the universe was only 300 million years old. Some of these galaxies are surprisingly massive and mature. They appear to have formed even faster than the Hubble objects. One particular galaxy, JADES GSZ130, has been confirmed at a redshift of about 13.2, meaning we see it as it was roughly 320 million years after the Big Bang. This galaxy contains perhaps 1 billion solar masses in stars. It formed in an astonishingly brief period. Other James Webb discoveries include galaxies with evidence of active galactic nuclei, central supermassive black holes actively accreting matter at very early times. The black holes appear to have formed almost immediately after the Big Bang, with masses that challenge our understanding of black hole seeding and growth. James Webb has also found that the early universe was more complex than expected. Rather than simple, primitive systems, the early cosmos contained diverse galaxy types, varied morphologies, and evidence of ongoing star formation and chemical enrichment. The picture that emerges is of a universe that matured far more rapidly than our theories predicted. Something enabled the formation of massive, complex galaxies in an extraordinarily short time, and we don't know what that something is. Now let me explore the specific theoretical proposals for explaining these observations. Faced with observations that contradict predictions, theorists have proposed various modifications to the standard model. Some are conservative, tweaking parameters within the existing framework. Others are radical, invoking new physics. The first proposal is enhanced star formation efficiency. If stars formed more efficiently at early times, if a larger fraction of available gas converted to stars, then galaxies could grow massive more quickly. This might occur if the gas conditions were different, perhaps denser, perhaps cooler, perhaps less turbulent. Some theorists propose that the first generation of stars was different from later generations. Population 3 stars formed from pure hydrogen and helium may have been more massive on average with different formation efficiencies, but enhanced star formation efficiency has limits. If too much gas converts to stars too quickly, the resulting feedback, radiation pressure, supernovae, stellar winds should disrupt the galaxy and suppress further star formation. The balance is delicate. The second proposal is primordial black hole seeding. Standard theory assumes that supermassive black holes grow from small seeds, perhaps the remnants of massive first-generation stars, perhaps direct collapse of gas clouds into black holes of a few thousand solar masses. But if black holes form primordially in the first moments after the Big Bang, before stars existed at all, they could provide much larger seeds for later growth. Primordial black holes of thousands or millions of solar masses would give supermassive black holes a head start, allowing them to reach billions of solar masses sooner. Primordial black hole formation requires special conditions in the early universe, perhaps large density fluctuations, perhaps phase transitions in the early cosmos. These conditions are speculative but not impossible. The third proposal is modified dark matter. If dark matter has properties different from the standard cold, collisionless assumption, the timeline of structure formation could change. Several alternatives have been proposed. Fuzzy dark matter, extremely light particles with wave-like behavior would suppress small-scale structure but might allow different formation pathways. Self-interacting. Dark matter particles that collide with each other would change how dark matter halos form and evolve. Dark matter with additional forces, perhaps a dark sector with its own interactions, could enable faster collapse and denser concentrations. Each of these alternatives has implications throughout cosmology, not just for early galaxies. They must be consistent with all observations from the cosmic microwave background to present-day galaxy surveys. The fourth proposal is modified gravity. General relativity is our theory of gravity, and it has passed every test we've subjected it to. But most tests are in weak gravitational fields. The early universe involved stronger fields and higher densities. If gravity behaves differently under extreme conditions, if there are modifications to general relativity that become important at early times, the formation of structure could be accelerated. Modified Newtonian dynamics, and its relativistic extensions have been proposed to explain galaxy rotation curves without dark matter. Some theorists have explored whether modified gravity could also explain early galaxy formation, but modified gravity faces significant challenges. It must explain all the successes of general relativity while also explaining the new observations. Finding a theory that does both has proven difficult. The fifth proposal is that we live in an unusual region of the universe. Perhaps our local environment is atypical. Perhaps the early galaxies Hubble observed formed in a region with unusually large density fluctuations, a cosmic hotspot that enabled rapid structure formation. This proposal conflicts with the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. If our observed volume is unusual, we cannot extrapolate from it to the universe as a whole. But the cosmological principle is an assumption, not a proven fact. The observed volume is finite. We cannot verify that the rest of the universe resembles what we see. Perhaps the universe is more varied than we assumed. Now let me discuss why this matters beyond cosmology. The crisis in early galaxy formation is not just a technical problem for specialists. It has implications for fundamental physics, for our understanding of the universe, and ultimately for our place in the cosmos. First, it tests our basic theories. General relativity and the standard model of particle physics are the twin pillars of modern physics. They have been tested with extraordinary precision in laboratories and observatories, but they have never been tested in the extreme conditions of the early universe. If the early galaxy observations require new physics, that new physics would modify or extend our fundamental theories. This could have implications throughout physics for particle accelerators, for gravitational wave detectors, for our understanding of the nature of matter and energy. Second, it affects our understanding of cosmic history. The history of the universe from the Big Bang to the present is one of the great achievements of modern science. We can trace the evolution of the cosmos from its first moments to the formation of galaxies, stars, and planets. This history provides the context for everything else, including the origin of the Earth and the emergence of life. If our understanding of early cosmic history is wrong, if galaxies formed differently than we thought, the entire narrative may need revision. The cosmos may be more complex, more dynamic, and more surprising than our current theory suggests. Third, it raises questions about predictability. Science works by making predictions and testing them against observations. The lambda CDM model made predictions about early galaxies, and those predictions appear to be wrong. This could mean the model needs modification, a normal part of scientific progress. But it could also mean that the early universe was somehow unpredictable, that initial conditions or stochastic processes led to outcomes we couldn't have anticipated. If the universe is less predictable than we assumed, our confidence in extrapolating from known physics to unknown conditions may be misplaced. We may need greater humility about what we can and cannot know. In part 2, I want to explore the deeper implications of these observations. What do they tell us about the nature of cosmic structure? What might they reveal about physics beyond the standard model? And how should we respond when the universe presents us with something that shouldn't be there but is? So we've established what Hubble found: massive, mature galaxies existing at times when they should have been impossible. We've seen how these observations challenge the lambda CDM model and examine the theoretical proposals for explaining them. Now I want to go deeper. What do these observations tell us about the nature of cosmic structure? What might they reveal about physics we haven't yet discovered? And how do we make sense of a universe that presents us with phenomena that defy our best theories? Because the crisis is not just about galaxies. It's about the fundamental question of how order emerges from chaos, how structure arises from smoothness, how the complexity we see around us came to exist at all. Let me begin by examining what we thought we knew about structure formation. The universe began in an almost perfectly smooth state. The cosmic microwave background, our snapshot of the universe, 380,000 years after the Big Bang, shows that matter was distributed with remarkable uniformity. The temperature differences across the sky are only about 1 part in 100,000. From this near-perfect smoothness, all the structure we see today emerged. Galaxies, galaxy clusters, superclusters, the cosmic web, all of it grew from those tiny initial fluctuations. The process is straightforward in principle. Regions with slightly higher density attracted more matter through gravity. They grew denser, pulling in still more matter. Eventually, they collapsed into concentrated structures, dark matter halos first, then galaxies within those halos, but the process is slow. Gravity operates at the speed of light. Information about mass concentrations cannot spread faster. The collapse of structures is limited by the time available. Large structures require more time to assemble than small ones. This is why the Standard Model predicts hierarchical assembly. Small structures form first because they require less time. Larger structures form later through mergers of smaller ones. The most massive galaxies should be the youngest, assembled recently from building blocks that formed earlier. Hubble's observations invert this expectation. The most massive galaxies appear early, not late. They seem to form rapidly, not gradually. They don't look like they assembled from smaller pieces. They look like they formed all at once. This inversion is what defies logic. It contradicts not just our models, but our intuitions about how gravitational assembly should work. Now let me explore what physical processes might explain rapid galaxy formation. If massive galaxies formed faster than expected, something must have accelerated the process. Several candidates exist, and each has profound implications. The first candidate is enhanced initial conditions. The tiny fluctuations in the early universe, the seeds from which all structure grew, are thought to have been generated during cosmic inflation. The properties of these fluctuations are encoded in the cosmic microwave background and determine how structure forms. If the fluctuations were different than we measured larger on certain scales, perhaps, or with different statistical properties, structure could form faster. Larger initial fluctuations would collapse sooner. Structure would appear earlier, but we've measured the fluctuations in the CMB with extraordinary precision. They appear consistent with the standard inflationary predictions. Either our measurements are wrong, or the fluctuations grew in ways we don't understand between the CMB epoch and galaxy formation. One possibility is that there were features in the initial conditions that we haven't detected localized regions of enhanced density, perhaps, or correlations between different scales that our analysis missed. These features could have seeded early massive galaxies in ways the smooth statistical description fails to capture. The second candidate is non-standard dark matter behavior. In the Standard Model, dark matter is cold and collisionless. Dark matter particles interact only through gravity. They don't collide with each other or with ordinary matter. This simplicity makes the physics tractable, but may miss important effects. If dark matter has additional interactions, if particles can scatter off each other, annihilate, or experience forces beyond gravity, the dynamics of structure formation would change. Dark matter halos might form differently, collapse faster, or achieve higher densities. Some models propose that dark matter interacts with a dark radiation component, light particles, that exert pressure and influence how dark matter clumps. Other models propose that dark matter particles can decay or annihilate, releasing energy that affects structure formation. Each of these models makes different predictions. Testing them requires observations beyond galaxy formation, measurements of dark matter distributions in nearby galaxies, searches for dark matter annihilation products, precision cosmological observations that probe dark matter behavior. The third candidate is early feedback processes. Stars and black holes produce energy, radiation, winds, jets, explosions. This energy can heat surrounding gas, blow it out of galaxies, and suppress further star formation. Feedback is crucial for understanding galaxies. Without it, models predict too many stars forming too quickly. But feedback can also work in reverse. Under certain conditions, the energy released by early star formation might compress surrounding gas, triggering more star formation rather than suppressing it. This positive feedback could accelerate galaxy growth. Early supermassive black holes might play a similar role. Jets from accreting black holes can heat gas over large volumes, but they can also compress gas in certain regions, triggering star formation. The net effect depends on geometry, timing, and local conditions. If positive feedback dominated in the early universe, if the first stars and black holes triggered runaway galaxy growth, the rapid appearance of massive galaxies might be explained. But this requires fine-tuning. Positive feedback can easily run away, producing galaxies even more massive than observed. The fourth candidate is primordial structures, perhaps massive structures formed even before galaxies, structures that provided the scaffolding for rapid galaxy assembly. During cosmic inflation, quantum fluctuations were stretched to cosmic scales. Most of these fluctuations were small, the seeds of ordinary structure formation. But rare, large fluctuations might have created massive primordial structures. These structures might include primordial black holes formed in the early universe before stars existed. If primordial black holes were common and massive, they could have seeded early galaxy formation, providing gravitational anchors around which gas accumulated rapidly. Alternatively, cosmic strings or other topological defects from early phase transitions might have provided sites for rapid structure formation. These exotic objects are predicted by some particle physics theories and could have cosmological effects we haven't accounted for. Now let me examine what these observations might tell us about the nature of time in the early universe. One of the most unsettling aspects of the early massive galaxies is the timeline problem. There simply doesn't seem to be enough time for them to form. The universe was 500 million years old when some of these galaxies existed. 500 million years sounds like a long time, but it's only about 4% of the universe's current age. Complex structures that we thought required billions of years appear in this brief window. Could our understanding of time itself be wrong? In general relativity, time is not absolute. It's part of space-time, woven together with space, affected by gravity and motion. Near massive objects, time runs slower. In different regions of the universe, proper time, the time experienced by local observers, might differ, but the time differences predicted by general relativity are far too small to explain the observations. The universe was expanding uniformly at early times. There were no massive concentrations to create significant time dilation. The discrepancy cannot be explained by relativistic effects within standard physics. Some theorists have proposed more radical modifications. Perhaps time itself behaved differently in the early universe. Perhaps there were additional dimensions that affected the flow of time. Perhaps the relationship between time and physical processes was different at high energies or high densities. These proposals are speculative, and none has been developed into a complete theory. But the observations are so challenging that radical ideas deserve consideration. Now let me discuss what the observations imply about the physics of the very early universe. The galaxies Hubble observed formed from matter that emerged from the Big Bang. The properties of that matter, how much there was, how it was distributed, what particles it contained, were determined in the first moments of the universe. If galaxies formed faster than expected, the initial conditions might have been different. And if the initial conditions were different, the physics of the very early universe, inflation, the electroweak transition, baryogenesis might have been different too. Consider inflation. The standard inflationary scenario predicts nearly scale-invariant fluctuations of similar amplitude across a wide range of scales. This prediction matches the cosmic microwave background observations well, but the early massive galaxies might require fluctuations that are enhanced on specific scales corresponding to galaxy masses. This could indicate that inflation was more complex than the simplest model suggests. Perhaps inflation occurred in multiple stages, with different expansion rates producing different fluctuation amplitudes at different scales. Perhaps there were features in the inflaton potential, the energy landscape, that drove inflation that produced localized enhancements. Perhaps inflation ended differently in different regions, creating variations we haven't accounted for. Each of these possibilities has implications for particle physics. The inflaton field, whatever drove inflation, is not part of the standard model of particle physics. Understanding its properties could reveal new physics at energy scales far beyond what accelerators can probe. Consider baryogenesis. Ordinary matter, protons, neutrons, electrons, is rare in the universe. For every proton, there are about 1 billion photons. The small excess of matter over